Hello, everyone. So today I'll talk about how Triton achieve different performance on AMD backend. So specifically, I'm going to talk about how MI350 achieve near peak performance right from the start, no warm-up needed. The story is about a shared compiler infrastructure and new hardware features, and how they come together with smart designs. Okay, so typically, when a new GPU launches, it takes months of kernel tuning to reach the full performance. But for MI350, this is not the case. So MI50 reaches near peak performance very quickly, and that is because the shared compiler infrastructure abstracts away hardware differences while still generating efficient code. So this is Triton's promise. So no warm-up needed, right? So as soon as the silicon lands, the AMD backend is ready to go. Okay, so the foundation has three key components. So the first is a generalized linear layout system. And the second is a flexible pipelining framework. Third is a set of shared memory utilities. So the generic linear layout system that unifies how tensor elements are mapped across AMD and NVIDIA backends. So that means for new GPU architectures, it can just reuse the same layout logic with minimum backend specific changes. The flexible pipelining framework supports multiple scheduling strategies across backends and workloads. And it also provides a structured model to express how memory and compute operations should interact. We also have a set of shared memory utilities for allocation, subviews, and general swizzling. So these tools automatically generates normal and transposed LDS shared memory reads, which can also reduce backend-specific code. So all these abstractions let Triton's compiler infrastructure scale seamlessly across backends and workloads. All right. Now let's look at the hardware improvements that make MI350 exciting. So compared to MI300, MI350 doubles the matrix instruction rate. It also introduces scaled MFMA instructions, which enables efficient quantized workload. The shared memory system is much larger. So now we have 160 kilobytes with 64 banks. We also plus new transposed instructions to read elements from shared memory and the larger vectorized direct to shared memory instructions. So these will facilitate cleaner pipeline design and implementations. We also have the new permalink instructions for faster intra-warp layout conversions and extended type conversion ops covering 32, 16, 8, and 4-bit paths. Okay, so these new features creates a much richer instruction set for compiler optimizations. On the software side, we leverage the shared compiler infrastructure to quickly implement new features. So the first one is the generalized linear layout system. So now the linear layout system shares code with NVIDIA backend. So this means it improves maintainability, and it also benefits from generic optimizations. The async copy to local ops are lower with direct to shared memory instructions. This helps with a cleaner pipeline design and implementation. It also reduces register pressure. The local load op lowering is also generalized to add support for linear and petty layout. It can automatically emit DS3 transpose instructions when needed. We also have petty shared layout, which is designed on top of the linear layout system. So this package layout can help us with register pressure and band conflicts. So finally, these layout conversion ops helps with intra-warp data exchange, and it also enables larger vectorized stores. Okay, so all of these build on top of the infrastructure we just discussed. So this demonstrates how we could quickly adapt Triton for MI350. Now let's look at performance. So this table compares the performance of MI350 against MI300 for the Matmul kernels. It uses the ships and the data types from last year. As we can see, we see a roughly 1.6 to over 2x speed up over MI300, and this is attributing to faster MFMA instructions and better memory subsystems. This table also compares Triton with HIP-LT on MI350. So HIP-LT is the AMD highly tuned Matmul library. There are two things to note. The first, so the Triton's focus is on MX, API, and the context kernel development. So this traditional 16-bit and 8-bit kernels are not heavily optimized yet. And the HIP-LT numbers are after auto-tuning, but while Triton's numbers are just out of the box compiler results. And even with that, we can achieve 70 to 80% of HIP-LT performance, which is quite impressive for a generalized performance, for a generalized compiler. And I also want to highlight the Triton performance on MX AP4 Matmul kernels at the bottom. So this is exclusively supported in Triton on MI350 with native instruction support. So on MI300, we can run the same MX AP kernel with emulation paths for scaled-out operations. Okay, attention kernel. So this table, compared to 300, so the 350, we observed roughly more than 2x improvement across common attention configs. So this comes from two major factors. So first one is the stronger MI350 hardware, right? Including the higher MFMA throughput and a better memory system. The second one is compiler level pipelining enhancement. So especially the inter-warp scheduling. So I'll talk about that in the next few slides. So these numbers demonstrate that the Triton's compiler pipeline can quickly leverage new hardware features and scheduling strategies. So again, this reinforces the theme of day one performance support. All right, so let's look deeper into the mechanism that makes all this possible. The Triton's flexible pipelining framework. The pipelining framework enables software pipelining, so in which the operations from later iterations of the loop will be prefetched into the current iteration, breaking dependencies and overlapping ops. So this framework provides multiple scheduling strategies. And for MI350, this is what enables the inter-warp scheduling mechanism. In this process, the Triton will assign ops to different stages and to different clusters, and then we will have a compute cluster and a memory cluster. Then the kernel will alternate between the compute and memory clusters from different warps. The LLVM backend will handle the fine-grained instruction interleaving within each cluster. So the collaboration between Triton and the LLVM enables efficient memory compute overlapping without any manual tuning for the kernel. Okay, so let's look at how inter-warp scheduling looks at practice. So the hardware can co-execute memory and compute operations. So we will have two warps. while one warp is doing compute, the other one is handling the memory. And they switch those. So this creates a smooth pipeline that all the hardware components are busy. This is achieved by Triton's clustered scheduling and ILVM low-level instruction interleaving. So this is a clear separation of responsibilities. Let's look at a concrete example of the inter-warp scheduling for FA v3 kernel. So this is the pipeline design. We have a 4-stage pipeline design for the FA v3 kernel. So we don't need to look at the details here. The idea is that the Triton can assign ops, right? Ops from the attention kernel to different stages, right? And inside the steady loop, we can further assign ops to different clusters, right? As a result, for this kernel, we have 4 clusters. So cluster 0 and cluster 2, they are the compute cluster. It contains softmax and the dot, right? Cluster 1 and 3, they are the memory clusters. They have they have memory operations from global memory or the shared memory. And the kernel will have 2 warps, alternating between compute and the memory clusters. So the result is at every moment of kernel execution, some warp is doing compute. And there's always a warp doing compute. So as a compute-bound kernel, this is the perfect state, basically. OK. This success comes from a well-scoped collaboration between Triton and the ILVM compiler team. So the Triton designs the high-level pipeline cluster, pipeline scheduling, and also it defines the scheduling boundary. And then ILVM will do the fine-grained instruction scheduling within each cluster. The result is a compiler hardware co-design that enables Triton kernels to be close to hand-tuned assembly performance. And this collaboration continues for future GPUs. To wrap up, okay, so Triton's linear layout system, the pipelining framework and the shared memory utilities abstracts away hardware differences. And these foundations enable the AMD backend to achieve very good day 1 performance on MI350. And the inter-warp scheduling mechanism extends these ideas to the next level of performance. And the ongoing collaboration between Triton and the ILVM backend ensures that for future GPU architectures, we can also get very good day 1 performance with Triton. So no warm-up needed. So as long as Triton will be ready when new hardware arrives. Thank you. That's the end of my talk. I can take questions right now.
So you showed a slide where the Triton Matmul, you said, had 80% better performance than Hiblas LT?
Yes.
Is that all upstreamed? Is that with the upstream Triton AMD backend?
Yes.
OK. Thanks.
I was wondering if you could give an example of a workload where you could compare native FP8 on MI300 with emulated MXFP4 on MI300, and what kind of comparison are you seeing there, if you have it? If not, that's okay.
Maybe I have offline, but I don't have anything on the slides.
OK, cool.
Yeah, sorry about that. OK, any more questions?
I actually have a question.
Yeah.
So, Triton was originally designed primarily with NVIDIA in mind. And I think AMD have done an amazing thing of breaking through that and making AMD like a primary target for Triton. I was wondering if you have any advice for those people in the audience who would like to also adapt Triton to other types of targets. What's the playbook? How do you break through?
Performance. There are three things: performance, performance, and performance. I think it's very simple, right? We have customers, and the customer care about performance, and that's it. Whatever you do, right? Performance is the only thing customer cares about.
So I think there is a few things to follow up on that. Basically, I mean, Triton has a particular program model, and you need to think about how that actually matches the program model. As also Phil mentioned at the beginning, that I mean, some of the hardwares might not fundamentally designed with that feature and hardware features. So even we can actually adopt it, it might be actually challenging to match some of the underlying hardware stuff. So it's more fundamental and kind of like throw the whole kernel stack and analysis on that. And also, Lixun had a good point on performance side. So
yeah, thank you, Lei. Yeah, I think the other thing is the maintainability. So we try to adapt our code base to the current code philosophy, just to improve the maintainability. That is very important.
Hi, I have a question about the last point. The second last point you bring up is the interleaving the warp.
Yeah.
As you know, like the LLM, some of the inference framework are using like mini batch to like using like two CUDA stream to overlapping between the workloads to make sure it's doing the compute all the time. Do you think with this interleaving using two warps, the mini batch is still like necessary things to have?
I think they are a little bit different, right? This is for just a single kernel, a single stream stuff. I think it depends on the hardware capability. Maybe it's always benefit to have multiple streams, especially if you think about larger things like multi-kernel or multi-GPU stuff. That should be beneficial. This is focusing on single kernel, single stream, and we are trying to utilize the last bit of the hardware performance we can get.
Just to follow up with this, what if we have two CUDA streams, and will this mechanism take into account that these two streams gonna compute for resources?
I think the general idea or the fundamental idea should be the same. We just want one thing to do the compute, the other one to do the memory. And this idea can also generalize to communication kernels, right? One thing is doing compute, the other one is doing communications. I think it's the same thing.
Okay.
All right. Let's thank the speaker. Thank you very much.
Thank you.